Okay, so we talked about the first energy level containing a 1s orbital, which could hold possibly 2 electrons, depending on the element that we're talking about. Let's now talk about higher energy levels, like the second energy level, level L. If you move out to the next energy level, the L energy level, we can represent that there are 4 orbitals that can be found at the second energy level, level L. Whereas only 1 orbital exists at the first energy level, 4 orbitals exist at level L. There's 1 spherical orbital that we'll call 2s. It's the second energy level, and it's an s orbital. So there's 1 spherical orbital in the second energy level, but there are 3 different p orbitals, dumbbell-shaped orbitals that we talked about, x, y, and z. And you can think of these as existing perpendicular to each other in 3 dimensions. Now, of course, this is not these axes, x, y, and z, are not fixed. They are tumbling around the atom as the atom exists in space. These are not fixed, but they are orthogonal or perpendicular to each other. So there are 3 dumbbell-shaped orbitals called p orbitals at the second energy level, and 1 spherical orbital level at the second energy level. And at the first energy level, we have 1 spherical orbital. And so if we were to look, for example, at the element neon, an atom of neon, here we have the nucleus. We have 2 electrons in the 1s orbital at the first energy level, and there are 8 electrons found at the second energy level, 2 in a 2s orbital, and 2 each for each of the 3 p orbitals that exist at that second energy level. And we can draw that as indicated here. So you can already determine immediately by looking at this, 10 electrons, you know that there are 10 protons in neon, and therefore neon has 10 protons, 10 neutrons, and 10 electrons found distributed as follows: 2 at the first energy level in an s orbital, 2 at the second energy level in an s orbital, at the 2s orbital, and 2 each found in each of 3 different p orbitals at the second energy level. So we've mentioned these energy levels. Let's discuss them a little bit more and point out that electrons that are found farther from the nucleus have more energy than electrons that are closer into the nucleus. And therefore, these energy levels increase in their energy, their overall energy, as you move out from the nucleus. So the first energy level has electrons with lower energy than energy levels that are higher up. So you would say, for example, that an electron in one of the 2 level orbitals, let's say an electron found in the 2s orbital at the second energy level, that electron would have a higher energy level than an electron found at the 1s energy level, found in the 1s orbital at the first energy level, K. So I'm going to re-emphasize this. Don't confuse energy levels that we draw as rings around the nucleus. Do not confuse those with the orbitals, which have complex shapes like dumbbells. This is simple as a sphere, but orbitals have, they're not simply rings around the nucleus. So don't confuse the energy levels that we draw like this with the actual orbitals that electrons are found in. And remembering that the electron orbitals are probability distributions where electrons are found. And the shapes of them describe the probability of finding electrons at different places. All right, let's recap then. We're looking at first 4 energy levels that are found in atoms going up to atoms with fairly low atomic numbers. The nucleus, the lowest energy level, second energy level, third energy level, fourth energy level, represented as rings here around this nucleus. And to reiterate, in order to raise an electron from a lower energy level to a higher energy level, energy would have to be absorbed. And if electrons move from high energy levels to lower energy levels, energy is released. And that will become important when we talk about the flow of energy in biological systems later. And to recap further then, we can represent these various energy levels in different colors, as on the previous slide. And here we'll combine that with the number of orbitals that are present at each of those first 4 levels. So here we have energy going up on the y-axis. And at the first energy level, there is 1 electron orbital, an s orbital. So the s orbital is present at the first energy level. At the second energy level, there is an s orbital as well, call that 2s. But there are 3 different p orbitals, x, y, and z. At the third energy level, we have that repeated, an s orbital at the third energy level, and then x, y, and z p orbitals. In addition, in the third energy level, we find d orbitals, and we're not going to really worry about those for this course. And then finally, at the fourth energy level, we see this as well, and we're not worried about d or f orbitals found at that energy level either. So finally, we're in a position now to look at the elements and their electron configurations and study how that is important in terms of chemical bonding, now that we have all the orbitals and the energies associated with those orbitals under our belts. So let's look at some elements. As we'll see, the periodic table is a way to organize the elements according to the electrons present in their outer energy levels, at the most outer energy level. We call those the valence electrons, and those are the electrons in the outer energy levels that are available for participating in bonding, in chemical bonding, bonding one atom to another atom. An element is non-reactive if there are 8 electrons in the valence shell, in the outermost shell. That would constitute a full shell for most of the energy levels that we're concerned with. And so we can refer to the octet rule and say that atoms actually kind of, thermodynamically speaking, like to establish completely full energy levels. Even though not all atoms have full energy levels, there is a force which would compel them to try and fill their outer energy levels. And this then determines how atoms will bond with other atoms. And we can look at the common elements that are found in biological systems. Carbon, oxygen, hydrogen, and nitrogen make up 96.3% of, let's say, the human body weight. So carbon, oxygen, hydrogen, and nitrogen are the most common elements found in cells. And then there's a remainder number that are found at higher than trace levels: chlorine, calcium, phosphorus, potassium, sulfur, iron, and magnesium. Some of these trace elements are actually very important in various roles in biological systems, as we will see. So now we can tackle the periodic table and look at some of these elements that are important in biological systems, indicated in green here. And we can look at the electron configurations for some of these elements, some of these atoms, and that will help us understand their bonding properties in forming molecules and biomolecules. So what I'd like to do now is draw out for you some electron configurations of these important elements in biology. And let's be sure we know what we're looking at here in the periodic table. The element name is indicated, the chemical symbol is indicated with large bold letters here, and the number refers to the atomic number. That is the number of protons present in each element. So let's start out very simply and look at hydrogen, and then we'll move to helium over here, even though it's not important in biology, just to get our minds around electron configurations. And then we can look at, for example, sodium, carbon, oxygen, nitrogen, if we want to. And maybe we'll look at chlorine as well. So let's draw out some electron configurations now in for these various elements. Let's start with hydrogen. So for hydrogen, its atomic number is 1, meaning it has 1 proton. And unlike the other elements, there's no neutron in the nucleus there. So it has one proton and one electron. Well, then we can draw this out as follows. We can say, okay, there's hydrogen, has one proton and one electron. So here's the nucleus. We can say, well, at the first energy level, which has an s orbital in it, there is one electron present. So here's the nucleus with one proton, and in the first energy level, there is one electron in an s orbital. That is the electron configuration for hydrogen. So then if we move to helium, let's say, let's look at helium here. Okay, it has an atomic number of 2. So let's draw that. So we have the nucleus here, and we have the first energy level, and its atomic number is 2, so there are 2 protons there, and there are 2 neutrons as well. And there are 2 electrons. And those 2 electrons are found in the s orbital at the first energy level. So we have the first energy level in the s orbital, and there are 2 electrons there. And that fills the 1s orbital. So if we move up higher now in terms of number of electrons for other elements, we'll have to we'll have to get to the second energy level. So this would be the electron configuration for helium, 1s2. That's not s squared. That means there are 2 electrons in an s orbital at the first energy level. All right, let's move on. Let's tackle, let's say, oxygen here. Let's look at oxygens. There are 8 protons, 8 neutrons, and 8 electrons. So let's draw its electron configuration. Before talking about oxygen, though, I want to point something out about the energy levels and the orbitals in them in terms of their energy. You'll note when we get to the second energy level, and this is mostly true for higher energy levels as well, that the s orbital has slightly lower energy than any of the 3 possible p orbitals, x, y, and z. And therefore, when we fill these electron orbitals, the s orbital will be filled first because that has a lower energy state, and thermodynamically speaking, lower energy states are always favored. So as we move up in electron numbers, as we go up the periodic table in elements, we would at the second energy level fill the s orbital before putting electrons in any of the p orbitals. Another thing to remember is that when each electron orbital, remember, only holds 2 electrons. But if you have 2 electrons, they will fill each of, let's say you have 3 electrons, they will fill singly the p orbitals here in the second energy level before another orbital acquires a second electron. That has to do with electron repulsion, basically. So here's how it would work here. If we added electrons going up the periodic table here, we would fill naturally the 1s orbital first, then the 2s orbital, then put electrons in the 2px, 2py, 2pz, and then go back to, say, 2px. Since these are equivalent energies, it doesn't really matter, but put another electron in 2px, then another electron in 2py, and then 2pz, let's say, although those could be any order that we wanted. So now let's move on to oxygen.